Alright guys, so one of the problems that you got to know how to do is how to find the apparent weight of an object if it's submerged in some kind of fluid. In this particular problem, we want to know the apparent weight of a block of copper if its real weight is 481 newtons and it has a volume of 5.5 times 10 to the minus 3 cubic meters. We're putting the block in fresh water and it's completely submerged. Now things to remember here. If the block's all the way under the water, it's going to displace a volume of water equal to its own volume. The buoyant force, according to Archimedes, is always equal to the weight of the fluid displaced. And we can find the buoyant force by using this equation. Buoyant force is equal to density times gravity, which is essentially going to give us, times volume. Density times volume is going to give us the mass of the water displaced. And when we multiply that by G, that will give us the weight of the water displaced. Remember that for water, for pure water, the density is 1,000 kilograms per meter cubed. So here's the thing. We're going to try to find the buoyant force. So we're going to go buoyant force equals the density of water, 1,000, times the volume of water displaced, which is going to be our volume of our block, which is 0.0055 meters cubed. And then we're going to multiply that by G, 9.8. So remember, this is actually being multiplied here. All three of these terms, this, and this, are all being multiplied together. And when we do that, we get 53.9. And remember that the buoyant force acts up. So we have 481 newtons, the weight, acting down, and we have 53.9 newtons, the buoyant force, acting up. The apparent weight is the difference in those two. So we're going to go 481 down minus 53.9 up. And that gives us an apparent weight of 427.1 newtons. That's what the block seems to weigh when it's underwater. Next thing we want to know, if the block is submerged completely and then released from rest, what's its acceleration? Well, this is where we just go back to Newton's second law. And we know that acceleration we can find using F net equals ma, which means A equals the net force divided by the mass. Well, in this problem, our net force is that 427 newtons down. 427.1 newtons down. And the mass of our object is going to be, take the weight, the regular weight, 481, divided by 9.8. So the mass of our object is 49.1 kilograms. So let's divide this out. 427.1 divided by 49.1. And what we end up with is an acceleration of 8.70 meters per second squared. And remember that acceleration is a vector, so that's going down. Or we could put negative 8.70 meters per second squared down. All right, hope that helps. Now let's go to the next kind of problem related to pressure and buoyant force. All right, here we have a diver going 25 meters below the surface of the ocean. We know the density of the ocean water, salt water, is 1025 kilograms per cubic meter. We want to know what gauge pressure acts on the diver. The gauge pressure is the pressure only due to the water, ignoring the pressure of the air above it. To find the pressure due to water when you're under the water, we're going to use pressure equals density times gravity times height. So in this case, the pressure, and again we're finding the gauge pressure here first, is going to be equal to the density of the water, 1025, times gravity, 9.8, times how far below the water the person is, that's the height, 25 meters. Multiply this out. And we end up with a pressure, a gauge pressure, of 251.1125. I got that wrong. I'm going to try that again. 251.125, and that's going to be in pascals, newtons per square meter. The second part of the question wants to know the total pressure. Sometimes that's called the absolute pressure. And that's equal to atmospheric pressure plus the pressure due to the water. And if you remember, at sea level, atmospheric pressure is 101,325. So we're going to take that atmospheric pressure and we're going to add that to the gauge pressure. So what we end up with for a total absolute pressure is 352,450, and that's going to be pascals or newtons per square meter. All right, here's another problem related to pressure. Here we have two objects, a sphere and a cube, suspended by a string and lowered into fresh water. They give us the volume of the cube and the weight of the cube. We want to know what the tension in the string is. So over here we have a cube. It's completely under the water. We know we have a weight on the cube of 50 newtons. That's acting down. We know we have a tension in the string pulling up. Now if there was no water there, the tension in the string would be equal to the weight of the object. But remember that we also have a buoyant force, and that's pushing up. We need to figure out how much that buoyant force is. And to do that, remember we're going to use buoyant force is equal to density times volume times gravity. So in this particular problem, our density it's fresh water, so it's 1,000 kilograms per meter cubed. Our gravity, or our volume rather, in this case is 0.0038 meters cubed. And then we've got to multiply that by gravity, 9.8. So if we multiply all that out, 1,000 times 0.0038 times 9.8. And we end up with a buoyant force of 37.24 newtons. And that's acting up. So essentially what you got to figure out here is that the tension is going to be equal to the difference in the weight going down and the buoyant force going up. So our weight going down is 50. So we're going to say 50 newtons minus the buoyant force, 37.24. So when we subtract that out, we end up with a tension in our string of 12.76 newtons. And that tension is going to be pulling up. All right, we've got one more part to the problem here. What we're going to do in the second part is we're given the dimensions of the cube. The cube's completely underwater. This time we know the tension, but we're trying to find the weight. All right, so again, let's draw it out. We know we have some weight, but we don't know what that is. We know that's acting down. We know we have some tension. And that tension is 21.6 newtons. That's pushing up. We also know we have a buoyant force pushing up. We don't know how much that is. And from last problem, you should remember that the tension in a problem like this is going to be equal to the difference in the weight and the buoyant force. So what we've got to find first is the volume of our cube. It's 0.2 meters on each side. And to find the volume of the cube, you know you go length times width times height. So 0.2 times 0.2 times 0.2. We end up with a volume of 0.008 meters cubed. That's the volume of our cube. And if it's completely underwater, that's also the volume of the water it's going to displace. So let's find a buoyant force. Remember, buoyant force is equal to density times volume times gravity. Density of water is 1,000 times the volume of the water displaced, 0.008, times G, 9.8. So we're going to multiply that out. And we're going to end up with a buoyant force of 78.4 newtons. So that's the force pushing up. Now let's find the weight of our cube. Again, remember that the tension is equal to the weight minus the buoyant force, which means the weight of this object is equal to the tension plus the buoyant force. But we know both of these numbers. We know that the tension is 21.6, and we know that the buoyant force is 78.4. So we add those together, and we come up with a weight of 100 newtons unit. All right, hope that helps. Got one other problem I want us to look at. In this one, we have a pipe. And the pipe is narrowing down, like so. We know that over here, the water is moving with a speed of 2 meters per second. We know that it changes from a diameter of 0.8 meters over here to a diameter of 0.2 meters over here. And we want to know what's the speed over here on this side of the pipe. What we got to remember is that the volume flow rate over here has got to be equal to the volume flow rate over here. And here, this is a big V. This is volume, not speed. So another way we can write that is we can write it as such. And this is called the continuity equation. A1 V1 equals A2 V2, where A is the area of the pipe, and little v here is the velocity of the liquid. So what we need to do first is find the area of both of those pipes. That's the cross-sectional area. Well, they're both pipes, so the inside area is going to be a circle. So for the 0.8 side, A equals pi. The diameter is 0.8, which means the radius is 0.4. Like so. So when we multiply this out completely, let's go 0.4 squared times 3.14. And we end up with an area of 0.5024 meters squared. For the smaller pipe, the area is going to be pi times 0.1 meters squared. Because again, the diameter was 2, which means the radius is was 0.2, so the radius is 0.1. Let's go 0.1 squared times 3.14. We end up with an area of the smaller pipe of 0.0314 meters squared. Now we can solve for area, or for velocity. In the larger pipe, the area was 0.5024 meters squared. The velocity of the fluid was 2 meters per second. In the more narrow pipe, the area was 0.0314 meters squared, and we're trying to solve for V. So we're going to divide both sides by 0.0314 and then solve. So 0.5024 times 2 divided by 1.0314. And we end up with a velocity of 32 meters per second. And that's how fast the fluid is going to be flowing in this small section of pipe. The last thing we got to figure out is what's the volume of water that will empty into the lake each second. Remember, A1V1 is another way of really saying velocity times time, because volume divided by time. Because remember, area times velocity could also be written as area times length over time. And area times length is volume over time. So all we need to do here is just solve for either A1V1 or for A2V2. Since we already have it written out right here, we know the area of the left-hand side of the pipe is 0.5024. We're going to multiply that by the velocity over there, 2. And that tells us that the volume flow rate, volume per unit of time, is 1.00 cubic meters per second. So your answer here, each second, 1 cubic meter of water flows through each side of this pipe and eventually out of the pipe. Hope that helps.